So we'll briefly talk about what a wave function is, and as I mentioned previously, exactly what a wave function is a matter of philosophical debate still among physicists. We know that this is some sort of mathematical function that represents our particle that has wave-like behavior, and really what we care about is, well, how can we use it to understand the properties of the particle? And so this wave function is a mathematical function that represents, it can be a complex function, and often is, mathematical function that, sort of represents the particle, whatever that means. And there's actually a lot of debate on one way of interpreting the wave function is that if we take, similar to a classical wave, if we take the intensity of the wave, or this would be like the amplitude squared of a classical wave, that kind of tells you how strong it is. In a quantum sense, what we take is our wave function. If we take that squared, or to be more precise, we take the complex conjugate times the wave function itself, often written like this with sort of an absolute value symbol around it squared. What this represents is a probability distribution of where the particle is. And when we think about wave functions, say something like orbitals in the hydrogen atom, when you've seen pictures of like an s orbital or a p orbital or a d orbital, what you're actually looking at is a plot of these probability distributions. And we will look at them in this class too, as well as the mathematical functions that are behind them. And so this probability distribution tells us, where on average we can expect to find the particle. It doesn't tell us exactly where it is, right? That would violate the uncertainty principle, but it tells us, what's the probability of finding the particle in a specific part of our system. In this case, when the particle in a box, is it in the left-hand side of the box or the right-hand side of the box? Is it in the middle of the box? Right? These probability distributions are, depend on the wave function. And so we need to know what this represents, because when we set up our system, we need boundary conditions, right? We need to understand, what's happening on, say, the edges of the box, specifically in this case. And so if the probability, right, the particle can't leave the box, we know that by definition, the wave function has to go to 0 at the edges of the box. Because the particle can't go into the walls, essentially, is what we're saying, because that barrier is infinite. So we need this information to be able to solve our problem. We need these boundary conditions to be able to solve the differential equation that we get. Just like we saw with the classical wave equation, we need boundary conditions to define our system, and these are the boundary conditions that we will use to represent our, or to solve our particle in a box problem.